So, welcome to the lecture 38 in this course. So, in this lecture we will consider the Hamiltonian for a charged particle in the electromagnetic field. So, we will construct Hamiltonian for a charged particle in the electromagnetic field. So, in last few lectures we have seen that how to construct Lagrangian through how to construct Hamiltonian from Lagrangian through Legendre transformation, and we have considered Hamiltonian for few simple systems. So, we have learned how to go from Hamiltonian to Lagrangian, the reverse process also. So, now we have good knowledge of constructing Lagrangian and Hamiltonian for a system and finding equation of motion. So, with this few remarks, let us move to the construction of Hamiltonian for a charged particle in the electromagnetic field. So, we will follow the same process as we did for earlier other examples. So, let us start with the Lagrangian for a charged particle So, let us have mass m and charge q in the electromagnetic field. So, we know the Lagrangian, let me write. So, in 3 dimensions, so it will have x dot, y dot, z dot and x, y, z in general and function of time. So, this will be kinetic energy half m x dot square plus y dot square plus z dot square minus q time phi, which is maybe function of x, y, z and t, plus q by c v dot a. So, v dot a we can write explicitly. Let me write q by c. C is velocity of light, x dot a x plus y dot a y plus z dot a z, and the potential phi and a, they are function of x coordinates and time. Okay. So, this is the Lagrangian, and we want to construct the Hamiltonian for this system. So, we will follow the exactly same procedure as to construct the Hamiltonian from a Lagrangian. I wrote down the steps. So, first Lagrangian is there. Now, we will consider the Legendre transformation. So, Legendre transformation to construct the Hamiltonian. Hamiltonian will be function of px, py, pz and x, y, z, and if you have time dependence in the Lagrangian, then possibly also function of time. So, Legendre transformation will be x dot px plus y dot py plus z dot pz minus the Lagrangian in the equation. So, let me write, this is my equation 1, this is equation 2. So, you have to use Lagrangian for equation 1. And then canonical momenta. So, we can calculate from the Lagrangian, for example, px is del L del x, all these are simple, and now you are familiar with this, and this canonical momenta will be, now if I differentiate with x dot, there are two places in x dot, one in the kinetic energy term and with the one and the vector potential. Okay. So, it will be m x dot plus q by c a x. Similarly, p y will be del L x dot equal to y dot p Py, so y dot, so m y dot plus q by c a y, and then we will have Pz is del L del z dot equal to m z dot plus q by c a z. So, let us write these are my equation 3. So, now we have to calculate the Hamiltonian, we have to simplify the right hand side using the momentum and canonical momentum relation with the velocities x dot, y dot and z dot. So, you can simplify the equation 3 to in this form, x dot equal to 1 by m p x minus q by c a x. Similarly, y dot will be on m p y minus q by c a y, and z dot will be 1 over m p z minus q by c a z. So, let us, this is my equation 4. Okay. So, now we substitute this in my Hamiltonian expression in the Legendre transformation, which is that stage it is function of both velocity and momenta. But in this point I like to mention that in this particular system, this canonical momenta is different from the mechanical momenta. So, this has different expression. In most cases canonical momenta and the mechanical momenta are same, but in this case I like to say the mechanical momentas are m x dot, m y dot and m z dot. So, when we need to calculate forces, you will have to change the rate of change of the mechanical momenta, not the canonical momenta. Okay. Okay, so, with this point let us write substitute equation 4 in the equation 2. So, Hamiltonian, so let me write in a smaller script. So, it will be p x and x dot. So, p x by m p x minus q by c a x plus y dot. So, y dot I will substitute. So, p y by m p y minus q c by a y plus p z by m p z minus q by c a z. So, this is the first term, and the Lagrangians were minus half 1 over m x dot square, y dot square, z dot square. So, if I substitute, so it will be half m v x dot square plus y dot square plus z dot square. So, it will be 1 over 2 m times p x minus q by c a x whole square plus p y minus q by c a y whole square plus p z minus q by c a z whole square. Okay. So, this is the kinetic energy term of the Lagrangian, and now you have, look at the Lagrangian back, you have minus q phi and then the vector potential dependent term. So, plus q phi minus q by c x dot times this. So, x dot if we substitute, it will be p minus x dot will be p x minus q by c a x times a x. So, let us write plus p y minus q by c a y times a y plus, okay. So, plus p z minus q by c a z. Okay. So, now all the terms of velocity has been eliminated from this Hamiltonian. Okay. So, what we did, we substitute equation 4 in the equation 2 to eliminate the velocities. That I have done. It's look little bit clumsy expression, but we can immediately see that some terms can be combined. For example, this term can be combined to this term px by same term. So, let us combine these two terms. So, Hamiltonian. So, if I combine taking a px minus q by c a x common and 1 over m, then first term will be px, second term will be q a x by c. So, it will be square of this. Similarly, I use a different color. So, this term can be combined with this term and it will give you 1 over m px minus q by py q a y whole square. Okay. And then similarly, this term will give you 1 over m pz minus q by c a z whole square. Then remaining terms are minus 1 over 2m px minus q by c a x whole square plus py minus q by c a y whole square plus pz minus q by c a z whole square. Okay. So, scalar potential term q5 plus. So, this is all term. Now, you can see again we can combine this term with this term, sorry, this term, and this term with this term, and this term with this term. So, if we combine this, we will obtain a very simple form. So, 1 over 2m px minus q by c a x whole square plus py minus q by c a y whole square plus pz minus q by c a z whole square, that is all, plus q times phi, the scalar potential, or in vector notation p vector minus q by c a vector whole square by 1 over 2m plus q times phi. So, this is the very simple and nice form of the Hamiltonian for a charged particle in the electromagnetic field. Basically, what happened, that the momentum is getting replaced by, so if you have a Hamiltonian of a system, then from that system you can find the Hamiltonian in the electromagnetic field by changing p going to q by c a vector potential which produce the magnetic field, and e going to the adding a q phi term. So, this is the vector scalar potential term. So, your Hamiltonian before magnetic field was p square by 2m plus, if it is Vx, then in magnetic field this Hamiltonian electromagnetic field p minus q by c a whole square plus v coordinate Vx plus say q times phi. So, this is the expression for Hamiltonian in the magnetic field. So, now you can find the canonical equations. So, canonical equation of motion, you can find So, that will be x dot will be del H del P x, y dot will be del H del P y, and z dot will be del H del P z. Similarly, for the other equation minus P x dot will be del H del x minus P y dot will be del H del P del y, and del y, and third equation or sixth equation rather, it will be del H del z. So, this sixth equation, it is 3-dimensional problem. So, you will get 6 equation in this system. So, I ask you to calculate this equation at least for a particular electric and magnetic field, and compare with the Lagrangian equation of motion, and you will get a equivalence between these two, and also try to find the Lorentz force law from the Hamiltonian. So, because you recall that when we calculate the Lagrangian, we started with the Lorentz force, and then we obtain a potential, velocity dependent potential, through which we can obtain the Lorentz force, and we succeed, and then we use that potential to construct the Lagrangian. Now, from the Lagrangian we have constructed the Hamiltonian. Now, we will see some example. So, example, let us consider the particle or maybe the electron. So, electron. So, for electron Q is minus E, okay. For electron, electron has negative charge. So, you can have for a particle in a particular magnetic field, say B equal to B0 in the k direction, and say in electric field E0 times x direction, suppose I direction. So, suppose you have this electric and magnetic field, then what will happen? Write the Hamiltonian for electron in this electromagnetic field. So, first step, you have to find the potential, because the Hamiltonian and Lagrangian are in terms of potential. So, first we will find the potential, and we have seen in last previous classes that for a uniform magnetic field along k direction, one of the potential, it can have infinitely many potential. One of the potential is minus B0 y by 2, B0 x by 2, and 0. So, one of the choice of the vector potential is this, and the scalar potential for this will be minus E0 x. So, these are the potential for this particular system. Now, we can write our Hamiltonian. So, Hamiltonian is H equal to 1 over 2 m p minus, let us say, p vector q by c a vector whole square plus q times phi. Okay. So, now it is mass of electron. So, 2 m e, and now if I write in components, so components px, then q is minus e. So, there is a minus, and then b0 minus b0 y. So, 3 minus, so it will keep minus again. So, e, or let me write mod of e to minimize your confusion. So, e by c, and then 2 b0 y, b0 by 2, okay, b0 by y by 2 whole square. Similarly, py again will be electronic charge is negative. So, negative, negative, positive, and this term also is positive. So, mod e b0 x by 2c whole square, and there is no component of vector potential along z direction. So, it will be simply Pz square, no changes, times, now times q phi, phi has a negative sign, q has a negative sign. So, we can have plus mod E E0 x. This is the Hamiltonian for an electron in the transverse magnetic field or magnetic field in k direction and electric field in the x direction. So, I will briefly comment about that how one can write directly from different system the corresponding Hamiltonian in the electromagnetic field. Okay. For that, let us consider hydrogen atom. This problem we considered earlier also. For hydrogen atom, then what will be the Hamiltonian? Hamiltonian for hydrogen atom will be the Hamiltonian for electron plus the Hamiltonian for proton plus the interaction energy of the system. So, this will be, there will be Coulomb interaction, so electrostatic. So, already we have written the Hamiltonian of electron will be 1 over 2 m e p e vector minus q by c and q will be plus the minus e. So, minus minus plus and then a vector of electron. So, vector potential for electron and vector potential for proton will be different because vector potential depends on position and electron and proton are in the different position. So, they have different coordinates. So, this whole square minus E times phi because electron has charge. So, this will be the Hamiltonian for electron. This we have written just a few minutes ago for a specific electric and magnetic field. Now, Hamiltonian of the proton will be 1 over 2 m p and then p of proton plus, now it will be minus because proton has positively charged. So, q c and then a of proton vector whole square and then plus e, or I am writing mod e of phi of proton. Okay. So, this is important that you have to write the vector potential and the scalar potential for different charge particles depending on that. This will be clear once we write explicitly. For example, the above electromagnetic field configuration that we just wrote few minutes ago, that your A is minus B0 y by 2 and B0 x by 2 and 0. So, electron, the vector potential for electron will be minus B0 y electron by 2, B0 x electron by 2 and 0. Similarly, vector potential for proton will be minus B0 y of proton by 2 plus B0 x of proton by 2 and 0. Okay. So, this one has to be careful. Similarly, for scalar potential of electron, scalar potential you remember it was minus E0 x. So, scalar potential of electron will be minus E0 of x electron. Similarly, scalar potential of proton will be minus E0 x of proton. And the electrostatic potential energy, if you calculate, then you will get the Hamiltonian for hydrogen atom in the electromagnetic field. Of course, you can simplify this by assuming proton at rest and electron is moving. So, in that case, the Hamiltonian will be simplified considerably, but this is the general way of writing. So, when you study in quantum mechanics the hydrogen atom problem, then you can solve the hydrogen atom problem, but now if you want to solve the hydrogen atom in presence of magnetic field, or electromagnetic field, you just simply replace your old Hamiltonian by this Hamiltonian in the magnetic field, and then you follow the same procedure to handle the additional terms and find the solution if possible for the field. Okay. So, in this way you can find. Similarly, for if you consider the example of harmonic oscillator, suppose we have a simple harmonic oscillator in say 3 dimension. So, 3 dimension it's and let us assume isotropic. So, frequency in x, y, z direction, frequency of oscillation are same angular frequency. So, this Hamiltonian is p vector square by 2m plus half m omega square, okay, half m omega square, and then you have x square plus y square plus z square. So, this is the harmonic oscillator for the this is the Hamiltonian for harmonic oscillator in 3 dimension. Okay. So, you can have this. If we consider this 3D oscillator in the electromagnetic field, EM field, then accordingly your P will be replaced by P minus Q by C A, and you have to add the electrostatic potential Q of phi. So, the harmonic oscillator in 3 dimensional space will be H equal to P minus Q by C A whole square by 2m plus Q times phi plus half m omega square x square plus y square plus z square. Okay. So, this is, and similar way that you can study your quantum mechanical problem by replacing without magnetic field Hamiltonian by a magnetic field Hamiltonian and study your harmonic oscillator. Later, in some application of canonical transformation, we will consider that harmonic oscillator in the magnetic field, how they can be solved through using canonical transformation. So, there we will consider this in detail. Okay. And for lack of time, so we will conclude that the Hamiltonian formulation, particularly the how to construct Hamiltonian for a system. So, we have seen many examples, particularly charged particles. So, we will discuss if you have tutorial class in the Hamiltonian formulation, but lack of time we will conclude this lecture here. In the next lecture, we will consider the Poisson brackets. So, that is an important topic, and how it is related to the how it helps the formulation of classical mechanics, that we will learn. So, in next lecture, lecture 39, we will consider Poisson brackets. So, with this, let me end this lecture. So, thank you all, and we will come back for the next lecture on Poisson bracket. Thank you.